Right, so just so you know what you're up for, we're about to rip into the lightning talks. If you saw it 2 years ago, you probably already know how it works. We've got 9 speakers who each get 5 minutes. They introduce themselves. They go 1, 2, 3, 4, 5. We're going to rip through all 45 minutes, 9 speakers, introducing themselves, their issue. They don't get a second less or a second more than 5 minutes. And then at the end of that, we're going to do 15 minutes of QA where we get all 9 speakers up to the stage and somehow you get a chance to ask questions across the entire group of everybody. And no doubt there'll be more questions in this time available for, so you'll have to follow them up afterwards. So to kick things off, I would like to introduce Olaf up to the stage. Very entertaining character, and we're very proud to have him here. And it's over to you, Olaf. Take it away.
Thank you very much. Good afternoon, all. It's a pleasure to be here. My name is Olaf, and I'm going to give you 5 minutes on the, wonderful world of 3D printing. And I thought the best way to do that was to give you sort of 2 examples of what it's all about. But just one slide about me and what I do. So I work for the Creative Design and Additive Manufacturing Lab, which I describe as a playground where companies, yourselves, can come and experience additive manufacturing firsthand. So open invitation to anybody here. If you're up in Auckland, swing by the labs and have a look at some of the toys. So 2 examples I'm going to give you, and the first one is a heavy-duty mainstream engineering example. This is an underground drilling rig made by Atlas Copco. So it's a tractor that goes into mines and drills holes. I think that's what it does. On the front of it, where that arrow is showing, there's something called a hydraulic manifold, which is used in just about any engineering equipment in the world. So for those of you not familiar, manifolds are basically blocks of steel with a whole bunch of pipes drilled into them to get fluid from one place to lots of other places. So that's on the front of that extendable boom arm. Atlas Copco is wanting to get into additive manufacturing, but not sure exactly what to do with it. So we redesigned it. It went from 16 kilos down to 1.4 kilos. That's over 90% weight saving. I mean, that is huge when you think about it. I actually brought one of them. I brought one of them here for anybody who wants to have a look at it afterwards, but that's it printed in my hand. So that's 1.4 kilos. Now think about it if you want to ship these around the world, the buy-to-fly ratio around that, or just handling them. So they were able to get rid of one of the big concrete counterweights on the back of the tractor by losing that weight on the front. Next example, which is a weird one, it's about medical modeling, so printing medical models for surgeons to use for surgical planning. But where it actually started is entirely different. It's to do with 3D printed guitars, which is one of my hobbies. And guitars are cool, so it's nothing like showing those. Now, these guitars are all printed in nylon, so it's a white plastic when it comes out of the machine. And they're hand painted, which, if I may say so, I think the only technical way of putting that, it's a pain in the ass. It's a hard thing to paint. So my wife lovingly paints the details of those, and she's got to reach in with a paintbrush. And because of that difficulty, last year I decided to have a go at seeing, can you print in full color? So full color has been around for a while, but I wasn't sure how well it worked. So this was the result of a guitar printed in full color. So that's straight off the machine. The only thing I've done to it is clear coat it afterwards. So I was so impressed by the quality of this printer and what it could do that I bought one. So we've now got one of these at the University of Auckland, so we need you guys to sort of push the limits of what you can do on it. But from this has led to medical modeling. So printing medical models that surgeons can use for planning and for explaining, for communicating better to the patient what it is they're going to be doing to them. And you'll see down on the table here one of the little sort of anatomically correct Barbie dolls that we've printed. Right now we're doing a lady who's got a tumor next to her spine, and we're printing this section of the body so the doctors can really plan how they're going to get to that tumor without hitting any of the organs. So that gives you a really, really good example. You'll also see on the table here an artery with a stent in it. This was for doctor communication, where they wanted to explain to the patient what it was that was going to be happening to them. So these are perfect tools for doing this. And because we can print in full color and clear plastic, we can embed parts in transparent material so you can really see what you're doing. Another obvious area of application. So color printing for civil engineering, for architecture, has been around for many years, but you've been printing in plaster of Paris, so gypsum powder, for those of you who remember the old Z-Corp machines. So we can now print in full Technicolor glory with windows, with stained glass, everything you want, all printed in full color, ready to go. So again, open invitation. What we now need is people like yourselves to push the limits of what we can do with the machine, find new application areas for the machine. So it really is, a serious open invitation for you guys to come by and visit the lab. Within the lab, we do a lot of work on light weighting and heat, increasing heat efficiency of heat exchangers, for example. So again, those of you with an interest in that area, in my bag, I've got a heat exchanger that is 70% smaller than a conventional tube and plate heat exchanger. So if you've got space as an issue, where you've got a small space that you've got to get something really efficient in, again, metal 3D printing might just be the right technology for you guys. So as I said, this was the 5-minute overview on the wonderful world of printing. It doesn't even scratch the surface of what you can do with it. But the role in our lab is to try to break the machines, to see how far we can push them until they fail, and then improve the process from there and find new innovative applications for it. So I'll leave you with that and hand on to the next speaker for the lightning round. Thank you.
Hello, my name is Andrew Blackford. I'm a structural engineer and I work in pre-construction for Naylor, design to construction. All of us have been through this evolution of turning our thoughts, drawings and specifications into the built environment. For some, and on occasion, it may not have been a particularly successful journey. Rightly or wrongly, this success is often defined by price. In particular, whether the price to build matches the budget allowed for. In my experience, it is rare that an unsuccessful project outcome is due to a structural design being too efficient or too heavy. Materials are easily quantifiable, and provided they are on the drawings, they will be accounted for in a project budget well before a contractor provides their price to build it. More commonly, it is what is not shown or what is unknown that leads to a poor outcome. This talk is therefore a request that you tell the story behind your designs and how you see them moving forward from the theoretical to the reality, from design to construction. No one will understand your design better than you, and if you aren't telling the story, it's quite likely that it's not being understood. In a traditional project delivery model, this is with your design team and in particular with your QS. In an ECI or D&B model, then it is with your contractor. Describe how you see the structure going together, whether the building will stand up on its own prior to being finished, or will it require temporary support? Does it meet the 6-month design life criteria while it is being built, or will it require supplementary bracing? Is the restricted access under that floor an issue until the props are removed, or is the space so lightly serviced that it doesn't matter that there's a delay? How do these services fit into the space provided and once the structure is installed, and will this require upfront, fully coordinated 3D modelling to ensure that it does? Why wasn't an alternative scheme that provides more flexibility presented? There will be a good reason. Often it is these intangible elements that can't be measured in kgs of steel or cubic metres of concrete that lead to a misalignment in expectation, a gap between what we perceived and what eventuated. The gap is not due to a lack of skill or thought, but a lack of communication. Often you will know exactly how you perceive the building going together. It's just that nobody else did. Terms like programming, procurement, construction, sequencing, temporary works front of mind when designing a new structure? Probably not. They are historically the domain of the contractor, but they can and are increasingly more significant in terms of their impact on the cost of construction. They should be being discussed during the design phase of a project. If you don't understand these terms, then who else in the design team does? Who is providing the advice and where is the knowledge coming from so the informed decisions can be made regarding buildability, duration and pricing? Contractors know this stuff, and without exception, they will share it with you. They just need to be asked. So should we be strengthening the links between engineers and contractors so that the relationships are there to foster collaboration and information sharing so designers can learn and designs are cognizant of these critical aspects of construction? In my opinion, the answer is yes. And so how should we go about this? At the individual level, one of the most beneficial things that you could do and should do is develop wide contact circles within the construction industry, whether this be with main contractors, subcontractors, or other consultants. Their views will be different to yours, and regularly seeking their input will enable you to develop a more holistic view of design. Talk to them regularly. Ask for feedback on present and historic designs. Don't be afraid to discuss your projects with contractors, even if the project hasn't come to market. There is really a commercial reason to prevent you from seeking advice. At the company level, question whether your designers have enough site time and the opportunity to build relationships and contacts with the wider construction industry. Consider reciprocal secondments with some of the larger main contractors. Most of them now have structural engineers on their payroll, and most would be keen to give their site engineers the opportunity to develop better design skills. At the industry level, do we provide the right training for engineers, and are there enough opportunities for contractors to present their views on designing and design practice? With better collaboration, communication and training, we can bridge the gap. Thank you.
Can a computer do my job? Yes and no. It's actually a loaded question designed to create an emotive response. And the answer very much depends on what aspects of your job you're talking about. I'm Bishop. I'm the Managing Director and Chief Entrepreneur at BVT Engineering, and we're using automation and AI daily. And as we change from vintage engineering methods to modern or AI-first methods, our engineers ask us lots of questions. Questions like, do I have a job once this algorithm rolls out? What about liability? What if the computer makes a mistake? How do I understand this? It's a black box. And perhaps a good place to start, they also ask, why bother? Why not keep using our vintage methods? They work fine, right? And I've got an important project due out tomorrow. Well, there's some good reasons around engineering skills shortages, increasing litigation and regulation loads, commoditising services, but by far the best reason is that AI-first methodologies are simply better tools in a number of fundamental ways. I'll go into that further, but first we need to ask, well, what is AI? It's not the science fiction killer robots that you see at the pictures. In its current execution, it's just a fancy way of processing data at massive scale and extracting the important relations between that data. For example, take a standard connection design, record the properties of that connection, the loads, the layout, the members, the bolt types, then record that same data across your company, across the industry. With that data, process through a neural network like this one, you get an algorithm that represents the combined methods of all the individuals. And then what could you do with that? Well, for example, you could build it into your quality control processes. And the algorithm would be able to analyse the connection you've just designed and output something like 90% of your colleagues would design a similar connection. Or the more scary alternative, 80% of your colleagues would consider this design to be under-conservative. We're all smart individually, smart enough to be structural engineers at least, but none of us are as smart as all of us. AI gives us a tool to actually leverage the hundreds of years of service, hundreds of years of experience we all say we have in our firms, and leverage it in a way that's applicable in day-to-day processes. And that's the first of the major advantages of AI. They can represent the combined learnings of all those previous engineering judgments. The second big reason is human error. We all have bad days, and not all mistakes will be caught by design, check, approved quality control processes. If humans were infallible, we wouldn't pay so much for PI insurance. AI can provide quality control that identifies in real time whether a particular judgment is outside of normal bounds. The third reason is speed. For example, there are numerous ways that AI tools can speed up process now, reduce admin load, and give us more time to focus on the really hard problems. So I'm going to assume that we get there, that we can move past, can a computer do my job, and onto how can AI tools help me to do my job better with less error and faster than ever before. What do we have to start thinking about in that world? So here's one thing. Currently there doesn't exist a standardized method of verifying the fitness for purpose of an AI algorithm. There's no ISO 9000 audit for AI. And there needs to be a bar for algorithm accuracy, for data set completeness, built-in resilience, and fail-safe methodologies. So we're working on that now. Clockwise from the top left there, we can use general risk management principles from ISO 31000 and the principles of machine safety design from ISO 13849, interweaving that with the limit state philosophies we're familiar with from 1170, plus some new tools specific to AI, like confusion matrices and solution space analysis. And we have the core of an algorithm verification method. Now, we're in the very early stages of this, so anyone who wants to collaborate on this with us, please feel free to get in touch. We're also going to do one more thing, and I'm quite excited about this one. As we move our current practice areas to API-enabled algorithms, we'll be releasing the corresponding engineering calculation methodologies free and open source under a Creative Commons license. We believe our colleagues should have the opportunity to review and comment on methods before they come up in live projects. And we think that's an important step in creating trust in AI-first processes, so look out for that before the end of this year. Thank you. I'm Matt Bishop. These are my details if you want to get in touch. It's been a pleasure.
Kia ora koutou, my name is Liam. I'm based here in Hamilton working for Beca. So I'm going to talk to you about the couple of weeks where Auckland stood still. So last year, in September 18th, a freak incident occurred. A high wind blew one of the trucks over and damaged one of the critical truss members, Diegel, which carried tension loads in the bridge. So yeah, a pretty crazy accident, never happened before, and I think it was a big challenge. And so the ASM, Auckland System Management team, which manages the bridge, includes Beca, Wakatahi, a few other Downer, a few other consultants as well on the team to spring into action. From the Friday evening straight away, the team was on site, undertaking inspections and surveys. So for those of you that don't know, the bridge is made of three superstructures. There's the original truss arch bridge in the middle, which carries 4 lanes of traffic, and then the 2 outer box girder clip-ons. And so the whole middle central section of the bridge was closed for 4 days initially, with only traffic in the outer lanes. So the damage was substantial. Full bending. Essentially, the member was put out of action. This was confirmed by at the bottom. All the bolts had shed, so no load path essentially in that member. What was the next steps? How are we going to? What sort of emergency response plan was going to be put into action? So over the night, the team there was assessing. Okay, well, how bad is this issue? What are we going to do? How are we going to fix it? Thankfully, Beca have been the structural engineer for the Auckland Harbour Bridge for over 20 years, and they've done all the existing strengthening, fatigue assessments, etc. So we've already got a model built of the existing bridge. They then said, okay, well, we need to assess the bridge to work out what is the new load path, where have the load's gone, how much has the bridge sagged. So the diagonal which was impacted was a tension member only, and actually was the lightest member, well, load-carrying member in the bridge actually, near mid-span. It was about 75 tonne of permanent load in that member. Then we thought, okay, well, we've got the whole model here already. Before we get the permanent member in, or to reinstate it back to its original capacity, can we reopen it prior to that with some temporary traffic? So we looked at, opening the bridge, so we looked at 2 lanes. So there was a period of about a week where 2 lanes of traffic on the middle portion were operating. And before, this is the 2 diagrams showing you've got secondary moments in the truss. And then on the right here, now with vehicle loads on the bridge, if we can have 2 lanes of traffic open, that member removed, you get a whole bunch of extra, much higher secondary binny moments, which we needed to assess within a couple of days. And that's where I came in. So the Auckland team led it all. Based in Hamilton, I was undertaking verification for it all. So, we needed, obviously, Wakatahi need to be sure that we're doing the right things. So I was the independent reviewer of this as well and assessing it. So there's a temporary prop went into position, which enabled those 2 lanes to be open and restoring some load path. The bridge had sagged about 35 mils from the member being pulled out. So that was a temporary condition. All the time they were working on a permanent replacement, so a box section to replace the existing one. And this was all, the dimensions were all on-site verified. Callums from up in Whangarei had fabricated this and did obviously on-site, in the yard trial assembly to obviously make sure everything fits. Then when the member was brought onto site on the 3rd of October, the 2 new members, they're separate members, and there was a connection in between with a post-tensioning rod. So the bridge had sagged. We needed to bring the bridge on the one side back up to its original position and restore all the dead load effects in the bridge. So this involved stress bar and jacking. So that was all done at mid-height of that diagonal member. And also we had on-site monitoring as well, with survey measuring it as we increased the load, what we were expecting to get. And then also all of the deflections were measuring up with our assessments as well. A load test was undertaken, just confirm everything was all good. No issues. That gave the confidence to the agency that things were back to normal. And then, at the end of a very long night, the team did a great job.
Thank you, Liam. Hello, everyone. I'm Nick Carman. Kia ora koutou, ko Nick Carman aho. Kia orana, bulavanaka, talofalava, kamatsu kayo, salamat potong, konnichiwa, ni hao, dobre utre, dobre den, salam alaikum, jambo, guten tag, goeiemorgen, bonjour, buongiorno, buenos dias, howdy, and g'day. Now, I've sucked up some of my very limited time just now to greet you in a variety of languages, despite what it says the topic is here on screen, but because what I really want to do is encourage as many of you as possible to learn just a few of the basics of a particular language to assist with our communication on your projects with clients and within our industry. This is the language of life cycle assessment and embodied carbon. So the power of communications come up quite a bit yesterday in the plenary sessions, and the idea that we work in a field where the ability to communicate our work on to others is just as important as the rigour that goes into our technical tasks is certainly not new. I've strong memories of Des imploring this point to me and my classmates at university several times, and it certainly remains true today, I think. Now, I'm expecting that several of you, or almost all of you in the audience, have experienced at some point in your life just how far you can get when travelling in a foreign country with a very few basics of the local language. Yes, no, please, thank you, hello, goodbye, 1 to 10, and a bit of good gesturing can go a long way. So here are some of the basic terms for life cycle assessment that we can become familiar with so that we can keep track of this topic and its relevance to us. Now, you have to forgive those who were in the afternoon session A yesterday. You would have seen this already, or those who have read our paper in the proceedings already. You can graduate on to reading the 8-page iStruct summary or the MB proposed frameworks, where you can see this diagram and study it further at your leisure. So, a couple of key terms. There are stages to a product and a project lifecycle. Those are stages A, B, C, and D. Those are broken down further into modules, which further define the categories in each stage in a little bit more detail. You've got stages A1 to A3, which are the product and materials. For structural systems, 75% plus of the embodied carbon is going to be associated with that particular stage. So a quick analysis on your different structural systems that you might be considering early on. Low effort, high impact in terms of the numbers that you're going to get out of that and their value to the rest of the project. Construction processes, our contracting friends can help out in that space, and a number of tools and average data sets exist for getting some of those. They're often a lot lower than A1 to A3, but they still exist. And then you've got the in-use phases where our MEP colleagues' operational impacts come into play, and then end of life and any other impacts outside of the system. So, and you can see on the bottom, cradle to gate, cradle to grave, cradle to practical completion definitions, which you can study when you look this table up later on. So there's an army of environmental scientists and others out there gathering the best data they can to sit in behind this for us to use, and it is country specific. So here in New Zealand, Brands is the steward of this, and collecting that information is a really big job. They've gone and done it for us. We don't need to do that. We need to use that to estimate the impacts of our design and our design options to help with our country's trajectory to reduce overall impacts. So in my version of this diagram, I include the business case and design phase at the start, which is really where everything gets set in train. And there are 3 simple tasks we can do in this phase. One is to do some back of the envelope calculations. Ask yourself a couple of simple questions. Do I know how big my building is in square metres? Do I know how much my building weighs? I certainly hope you do. Can you break that down into the requisite weights of the primary materials? Great. Take those, times them by some very simple, by some available carbon factors, add those up, multiplication and addition, and you've got your embodied carbon estimate for that scheme, for whatever LCA stages you've chosen to do that for. Task 2 is take another 20-30 minutes and do that for the alternative structural system, floor, foundation, or whatever that you might be interested in. Task 3, communicate that back to the wider project team and assess what you're going to do with those results alongside the cost, program, safety and other project drivers that you've got on the table, and encourage someone else to do it for services, facade and fit out, or step in and do it yourself. The free tools listed at the bottom can help, and I just want to finish saying that curiosity about things work is what we do, how things work is what we do, so let's get into it.
Kia ora everyone, I'm Annie Scott, a structural engineer working for Jensen, McArley, Austin, based in Auckland. I've been working for 6.5 years, 4 of those based here in New Zealand, and 2 years based in the Netherlands. So ensuring clear and concise communication is one of the most important aspects of structural engineering. At the end of the day, our structural engineering designs are primarily communicated through structural drawings. Pages of hand calculations, analysis models, and spreadsheets all go into creating the content for these drawings. But if the drawings aren't clear, if they don't convey the story, or if they just don't look professional, then what's the point? I want to share my view on why a good drafter is invaluable. Now, don't get me wrong, understanding key engineering concepts, producing correct calculations, and having a good review process is imperative to getting these drawings right. The buck stops with the engineer and the PS1 signatory, and you can't get correct structural drawings without correct structural engineering. But you also can't get good quality drawings without a good drafter. I believe that a huge part of completing a project successfully comes from having a good drafter by your side during the entire design process. I was lucky enough to be paired with some senior, incredibly talented drafters during my first few years of work. They questioned my designs, helped me visualize details, and pulled me up when they thought things were incorrect or when they knew there was a better way to do something. And it's this two-way, collaborative relationship about engineering that I love and believe needs to be encouraged. I want to emphasize this point, how important it is to pair a junior engineer with a senior drafter. Paul Campbell spoke yesterday about the importance of mentoring, and I think that drafters can be a huge part of this mentoring process. I've talked to peers prior to this presentation, and they all agree with this point. I'm not good at visualizing 3D and at visualizing things in 3D. It's not one of my strengths. But if I can sit down with a drafter, fly through a Revit model, who can turn architectural layers on and off, cut sections, help me work out details, help me work out levels, then this is a huge advantage. Another example is reinforced concrete moment frames. You know, you design your beam column joints early on, and then you finalize your column reinforcing, finalize your beam reinforcing, get back to your beam column joints, and suddenly nothing fits. And this is an area where drafters can provide so much expertise to help with that geometry. So as a young engineering graduate, let's be frank, you don't really know a hell of a lot. You learn so much on the job in those first few years, especially the practical side of engineering. You know, John here spoke yesterday about how as engineers we can now design things that can't even be built. And this is an area where I think drafters can really provide a lot of expertise. They can help make sure your designs are buildable in both a cost-efficient way whilst maintaining some degree of practicability. I've also recently experienced how time valuable a good drafter can be. When you're not having to mark up detailing inconsistencies or incorrect terminology, you can focus on the engineering, which, let's be honest, is time-consuming enough. At recent conferences, we've heard a lot about diversity of thought. We've heard from insurance brokers, mayors, property owners. So why not get drafters involved in this conversation too? We had Tristan Lamberts, a senior drafter, speak at the NZSCE conference earlier this year, who talked about using point clouds to help understand geometry of existing buildings better. And it was a really interesting presentation that I learned a lot from. So as BIM and technology continues to advance, clients and contractors only expect more detail, more collaboration. Drafters are being relied upon for so much more input as part of the design process, especially on large complex jobs where part of the challenge is just figuring out the geometry. So as we expect more from our drafters, having a good working relationship, good training programs, and including drafters in technical development is so important. It seems bizarre to me that the industry doesn't have more training or more courses for structural drafters. The learnings need to be a two-way street. Looking back on the jobs I've been a part of, I can honestly say that the ones that have been the smoothest sailing and the most successful are the ones where I've had a talented drafter by my side. It's time to start recognising drafters as key players in the delivery of quality engineering. Thank you.
So the innovation and technology is really accelerating the pace of change in our industry, in our society. And I'm here to tell you it's not going to stop. It's going to keep on increasing. And so the pain that we might feel, the changes that we might feel, are going to keep on happening and happening at a faster and faster pace. I'm Robert Amor, I'm a computer scientist from the University of Auckland, and I'd like to talk to you about what we see coming from a computer science perspective over the next 10 years and the sorts of impacts that might have. So we know technology is accelerating. The amount of technology, the impacts of that technology over the decades. Someone from 100 years ago just wouldn't recognise our world today. My students don't recognise the world that I came from. But it's not just society that's changing. Technology is changing in our industries as well. So the accelerated change, though everyone says our productivity is bad and our uptake of technology is bad, we're still seeing a huge amount of technology coming into the industry and impacting on this industry. So what sorts of things are you going to be hearing about, do I think, over the next decade? So digital twins, this really is the next generation from building information models. At the moment, something like 68% of our projects are using building information models somewhere inside the project, but BIM is really just a starting point, and digital twins is one of the successes that we're going to see from the BIM models. And so what does this give us? It gives us a replica of the physical world. The digital world can impact on the physical world, so decisions that we make in the digital world will modify what's happening in the physical, and the digital models are informed by what's happening in the physical world. As we get more and more sensors, and more data is going to come through, we can do more accurate simulations and analyses and join those two together. Many countries are looking to create national digital twins. New Zealand's looking to create a national digital twin. All of our three waters, all of our horizontal infrastructure, much of our vertical infrastructure will be available inside one model, a digital model of New Zealand and the infrastructure in New Zealand. We've heard already about artificial intelligence, and I agree completely that this is a support tool for humans, but what I'd like to point out also is that as artificial intelligence makes steps towards understanding a technique, it makes those steps incredibly fast, and it will get to beyond human abilities, becomes superhuman, and it becomes superhuman very, very quickly. So you would have heard how Go has been mastered. That, as you can see in the chart here, 36 hours learning to become a Grand Master, and after 40 days there's no human who's ever going to play Go and beat this machine again. Google can tell you what is a cat and what is a dog. How cool is that? But for our industry, wouldn't that be useful if we could say what sort of worlds we have and whether there are defects in those worlds? Whether there are deformations in the beams we have, deteriorations or discontinuities. All of those things would be possible with training data and be able to assist us in the jobs that we're working on. The work in natural language processing is giving us ways of being able to process human text and provide that to computers to be able to compute. Here in New Zealand, we've got a project which is trying to computerise all our codes and standards, 600 of them available for consenting in New Zealand, and put those into a form that a computer can actually run the codes and the rules inside those codes. Automated code compliance checking is, now that we have these building information models and that we have the codes, available. We can run the same processes that the council does to ensure that the building is going to meet the standards which we have inside New Zealand. There's a couple of companies working on this in New Zealand, working with the councils to be able to run their processes. And so you can give them a BIM model and they will tell you whether that BIM model is compliant or not with many of the codes and standards that we have in New Zealand. It can also be sent back to you so you can tell before you give it to the council whether you're providing the right information and whether it's going to be compliant or not compliant, and save you a bit of time at the council end. Thank you.
Ko mā tātua me nā Captain Cook nā waka, ko mōtiti tuku mōtere, ko te hinga o te rā, te whare tūpuna, ko Anthony Hoete tēnei. Kia ora, I'm Anthony Hoete and I'm a Professor of Architecture at the University of Auckland. I also was lucky enough to go through the School of Engineering some years ago. I'm going to talk to you about a tale of two whare. We all recognise the Māori whare. And this one is Hinamihi or Te Ao Tāwhito, which is Hinamihi of the ancient world. And in this next sort of 4 minutes or 45 seconds, I'm going to show you the transition of the whare from a cultural and visual object into the whare as being a technical object, which was lost with the arrival of Europeans when screws and nails and fixings turned up. But first, here's Hinamihi near Te Wairoa, near the pink and white terraces. And she was built by a rangatira who wanted a slice of the burgeoning tourist trade. This is Hinamihi after the 1886 eruption of Tarawera, and destroyed not only the terraces, but you can also note the sort of volcanic ash on the roof. In 1892, Lord Onslow shipped and shopped Hinamihi as a souvenir back to Clarendon Park. So this is the whare in Surrey. And you can see in this time she accumulated a thatched roof, which was a misreading of the photographic previous image of the volcan ash. But nonetheless, this talks about how accumulated history has a value. You might have heard me say she. In Māoritanga, the house is an ancestor. We talk to the house before we talk to those before her, which in the spirit of Dr. Dolittle is seen as madness from a Western perspective. But this is a way of keeping the house alive. So this is the whare is living heritage. And this is the whakapapa or genealogy of the house. This is the house today, unfortunately. This is Hinamihi. The carvings have deteriorated due to a lack of care, and such that they've been removed from the whare. And as you can see, 5% of the material which constitutes the carving is actually 100% of the identity, which required me as an architect to design a pathway and navigate a method for getting those carvings returned to New Zealand in exchange for an export whare. And so this is the architect lobbying to the Prime Minister, who was the Minister of Arts, Heritage and Culture at the time, to get the British, there's a national trust with their 5 million members, to the negotiating table. Quickly, I'm going to move on to Tāne Whirinaki. Tāne Whirinaki doesn't stand anymore. He hasn't stood since the 1931 earthquake. And I'm working with Mātua Jason on getting this piece of heritage back up. But when we put Tāne Whirinaki back up, it'll be predicated on boat building. So when those waka first arrived from our Pacific origins, the house was, the boat was upturned, and so the origins of the whare lie in a post-tensioning system which has disappeared and endangered. And also in that voyage across the Pacific, the waka was used to navigate, and this is quite timely given we're entering the period of Matariki. So you can see from Cook's journals that the form of the whare at the time was much more arched. We know the whare today is a gable, but it actually was arched, and it was arched because the heke or the rafters were cambered, and they were cambered using harakeke and rope, kwa, and tensioned back down through the ground. And this is by my colleague Jeremy Treadwell, which details how the connections were made and post-tensioned of those pre-cambered heke translated to foundation. And this slightly delightful non-BIM sketch shows, gives an imagination of what might have been, what process might have looked like. And this is a scale model replica being tensioned at the School of Architecture. So that is the whare, is the House of Technology. Kia ora.
All right, g'day everyone. I'm Patrick Cummeuskey, Technical Advisor for Auckland Council's Building Control Department, and with some of my other hats on, also involved with Civil Defence at Auckland Council, and in what free time I have a paramedic with St John Ambulance, so a few different things that I do. Today I'm wanting to talk a little bit about interdependencies between critical buildings for post-disaster operations, something that with a bunch of my hats on I have an involvement with. So a little bit of a snapshot of that. So to begin with, just want to talk a little bit about the operations themselves. So we have a range of organisations that either through legislation, through contractual arrangements, or even just through general sort of expectations by the public, provide services whenever we have disasters. Again, St John, for instance, being a good example of that. However, what we are finding these days is that through increased population growth, piecemeal urban planning and underfunding with our infrastructure, that a lot of these agencies are finding it more and more difficult to provide services to the community, even on a day-to-day job, day-to-day sort of situations. So for instance, when I started 15 years ago as a medic within St John, we would average around about 4 to 6 jobs per shift. These days, 8 to 10 is far more normal, and then if you think on top of that, whenever we have a disaster, workload can go up considerably, a lot more challenges. We are also having to contend with shifting modes of property management where there's an increased focus on being leaner, so making do with what assets we have, even selling those off, focusing on hub and spoke type models, so we become a lot more reliant on far fewer assets. And then add on top of that when we have challenges around the quality of construction, even of modern buildings, which those of you who were here 2 years ago at the previous conference may remember my talk back then, that we end up with potential vulnerabilities to these networks. So looking at some of this, we have across these networks not just the individual buildings but the reliances that they have upon each other. So an ambulance station, for instance, doesn't operate by itself. It relies upon communication centres, relies upon workshops, medical stores, and then it relies upon the buildings operated by various other agencies. So it's, one of these buildings is not an island unto itself. So feel that there needs to be a lot more attention given to how these networks operate. We've obviously done a lot of work into the horizontal networks, but more can be done in the vertical space as well. And on to vulnerabilities. So again, from talks that we've had across previous conferences, particularly in the last 10 years, with the spate of earthquakes and other disasters, it's shown vulnerabilities in the horizontal networks. For instance, even in government buildings which haven't been able to fulfil their own duties. We've had, again, within St John, buildings that have not been able to fulfil their functions, had to relocate to temporary structures, and even emergency operations centres that through, for instance, the failure of secondary systems have not done what they've intended to do. And just as an example, with the recent tornado that we had in Auckland, even though relatively small scale, even that has shown that the impact on a small portion of the city's building stock can have quite significant flow-on effects. So what I'm wanting to try and get to is, again, an encouragement that particularly for those of you who are structural engineers, that you have opportunities to encourage greater resilience be considered by the organisations that are operating these facilities. That we look where buildings can be built to a higher standard, that there's additional capacity within these organisations' portfolios in case failures do occur, and that where other vulnerabilities exist, that we are putting that effort in. And then going a bit beyond that, for those of you that are involved in governance type roles or ones where you have linkages in, particularly with policymakers that use your respect, use your positions to again advocate that we really want to see a far more resilient built environment out there, which hopefully will mean that when we do have the next disaster, that our emergency services and other organisations can continue to operate. Thank you.
Right, well, first, I just want to let you all know that every single one of those speakers nailed it within about 2 or 3 seconds of exactly 5 minutes. So, stunning result, team. If I could get all the speakers kind of rounded up here in a mob, it's a bit of a free-for-all now, right? So, we're going to hoist out the mics, and you can kind of just say, I got a question, and it's for Bob, Mary, Fred, or whatever. So,
Matua Anthony, thank you for your presentation. It was very inspiring. I guess from that, I'd just like to ask, what would you recommend us to take as a few first steps to take our knowledge from, tangata whenua, how can we as structural engineers incorporate that knowledge best?
Sorry, how to capture your knowledge?
Yeah, oh sorry, it wasn't loud enough. How can we as structural engineers best capture the knowledge from tangata whenua and incorporate that into our daily activities?
Sorry, there you go.
So there's 2 reasons which I think are important to capture to post-tension whare. First of all, it's endangered knowledge, and it shows that the very image of the house we see today is an aberration, and so it's about heritage. But the second thing is marae are places where you go in times of natural hazard, and so they have a sort of resilience, and by post-tensioning you can use things like seismographs to monitor the house and allow it to respond and be kept alive. And I think as engineers, I'm working actually closely with this guy to get that house, Tani Wharenaki, back up, and in that process we will be using seismographs, post-tensioning, digital carving techniques, and so again it shows how the traditional practices can also move ahead and be innovative moving forward. And so that's very much an engineering as well as architectural project. Kia ora.
okay, more questions? Okay, great, we'll do that then.
A question for Liam. Given obviously the exposure that was sort of come to head when that bridge girder or tie was damaged, has Waka Kotahi got you back to look at what would happen if a more critically loaded or more heavily loaded tie was damaged in a similar event?
Is it working? Yes. So there is ongoing studies around vulnerabilities of the existing bridge and what can we do to actually mitigate impacts. Where that goes, I think, is to be confirmed, really, from my understanding. But there's some ongoing work.
Would we have got such a fortunate outcome, do you think, if it was a more heavily loaded bridge? Or?
Hard to tell. I think we assess structures and we assess them with what we know. It is fairly redundant. Well, it's non-redundant, but it is. I guess to say, durable, or it can spread load as well, and it did that to the other truss as well, actually. Yeah. Who knows? Yeah, you don't want to think about it.
Okay, question over there, Gary. So somehow we've got to get the cube.
It's over here.
Okay, rip into it.
We're moving fast. I just have a question for Nick, and it's something I talked about at a tea break with you. Obviously, there was a session on embodied carbon yesterday, and some really good presentations. But one thing that wasn't really mentioned was circular economy at all. So when you basically are going to reuse, recycle materials, the embodied energy of a building drops quite considerably if you're looking into longer term and reuse of the materials, recycle. If you go to your waste management pyramid, it's reduce, reuse, recycle, recover energy from, and the last case scenario is disposal. So I just question a little bit just about using embodied energy solely as a measure of sustainability. If you look at maybe most buildings are designed for 50 years, you've got a service life a lot longer than that. I would think in 50 plus years, steel is easily going to be recycled here in New Zealand, and a lot of other technologies could be reprocessed or recycled at that stage. So I just want to know your opinion on that, or if you believe that after what I've said, if embodied energy is actually the right path.
Thanks, Gary. Those who caught the talk yesterday, certainly we're not advocating for embodied carbon to be the sole determiner of decision making on processes. We just think that it needs to be measured and on the table and part of the decision making. So that's point number one. Point number two, with regards to circularity, yes, I fully expect that over the coming decades we move to a more circular economy from a materials perspective and from lots of other systems, not just construction. We're not there yet, so it's not reflected in the data. So the data that we have to use at our fingertips today is reflected of the end-of-life disposal processes that happen with materials today. And so that, for example, steel doesn't get recycled in New Zealand. It goes on a ship 10,000 kilometres or something and gets recycled somewhere else by, sometimes dubious methods. So that's reflected in the data at the moment. And if we use the data we've got today and not what we imagine the data might be in 20 or 25 years, then we make decisions today on that basis. But designing our buildings so that they're available for inputting into a more circular economy in 25 years is definitely something. So I know there's been some discussion about whether there might be a way to incentivise design for disassembly over other ways of assembling buildings in a way that they're easier to reuse. And just finally, the LCA framework talks about your project and any possible recycling benefit sort of sits outside the bounds of that project as could be used by another project in the future. If you're coming along tomorrow and repurposing a project, repurposing a structure or large parts of it, then you get all of those materials for no embodied carbon. So example is the Mason Brothers building down in Wynyard Quarter in Auckland that repurposed a large part of the fabric of the original 1920s warehouse, and it got all of that material for no embodied carbon because it was repurposing it rather than tearing it down and sending it off to whatever process was going to happen or to disposal. So it's hard to capture it when you're designing a new project with the processes and data we've got right now, but when you're looking at how you might repurpose a building or large parts of materials into the start of a new build, you can get effectively a benefit by looking to find what materials you can incorporate into the project that already exist. Hope that helps.
I would still think it makes sense to look towards the future where the materials can be recycled here. So that's just my thoughts.
Yeah, I'd agree with that. And hopefully, with a few collective heads around the table, we can work with government and our other partners to figure out what the best approach for that is. Don't think you and I are going to figure it out today over the course of a microphone exchange, but I'm sure we can keep having a crack after this.
Okay, I'm going to leap in with a question of my own. This question's for Robert. So, Robert, I'm very interested in this idea of digital twins, and throughout this conference we've seen a number of different speakers talk about BIM models. So it seems clear to me that there's plenty of them out there, but what I'm less clear on is how people with their own intellectual property and their own client, etc., are somehow going to give their BIM model over to a national archive of BIM models. How's that all going to play out somehow?
You don't want to give us your BIM models? Oh, man. Well, I guess part of the way it plays out is that already you give your models, you give your plans to the council, and the council make those plans available in a broader way. You pay $5 per CD and you get a plan. So all of the infrastructure, all of the buildings which are consented will be available through the councils in some form already. So some things will happen that way. The major players, so Three Waters and Waka Kotahi and others are already talking about how they make available all of their information into these models. Obviously, not all of it is, so there is security and there's privacy, and not all the information will be available for everyone. You don't want everyone to know where the dams are and how you might attack them or blow them up. There is sensitive information. Not all buildings in New Zealand you're allowed to know where they are or what they do. So there are levels of privacy and the levels of information that will be made available. The UK has taken a really huge approach to how you would make a national digital twin. I hope we never go down that line because it's enormous and it's going to cost them £64 million to get just the infrastructure for a digital twin. But there are easier and simpler ways that we could have access to the right information and ensure that it's held in the right forms. So not everyone can see everything and just the right people get that access. We're computer scientists. We can find a solution to every problem.
Thank you. Okay, more questions? Oh, look, we're speeding up. Okay, should we throw the cube out from there? Nick, you want to hoist the cube over to them? Okay.
Yeah, absolutely. We've got about 15 of them in the lab. We've got printed drums, keyboards, and guitars and basses. So yeah, full 3D printed band. So yeah, welcome to come by and give them a play.
Cool. And there's another question over there somewhere, yeah?
My question's for Robert. We've seen in the news, especially with Waikato Hospital and the like, the susceptibility of our computer systems to overseas hacking. Doesn't this digital twin create susceptibilities for that sort of interference?
Yes.
How is that going to be addressed since it's the critical infrastructure?
Yeah, it is. And seriously, as with the UK National Digital Twin, they have a very serious security layer over the top of that to ensure that only the right people can get to the right information and it's held in a secure way. The New Zealand ones are looking at that as well. But the fact is, as you can see, almost everyone can get hacked. It's pretty impossible to stop a determined attacker getting at your information or locking your information away. But the best practice, and we will try and make sure that they can't get to that. They can get to it already through all of the distributed systems which exist. So, a collated one will have better security. Hopefully they manage that right.
Okay, we've got time for a couple more questions.
Thanks, everyone. My question is about two subjects. Actually, we know many of the countries, they have the codes or guidelines for civil defense and for structural engineers, for post-disasters and those stuff. I'm not sure if, at least I'm not aware if we do have a code or guideline for the structural engineering and buildings for civil defense or after natural hazards. But my question is about the Harbour Bridge in particular. Probably if you have a vital road or if there is a crucial network for after disaster, Harbour Bridge would be part of that one. How does it fit for that purpose? And if we have considered or we have check that one, the resilience in that building, and if it's going to withstand after a natural hazard. I don't know if it's a tornado or if it's a tsunami or earthquake. Thanks.
That was for me.
For you and for...
Yes, I guess you're asking about resilience of your major assets. I know personally that the Auckland Harbour Bridge has been assessed for seismic and strengthened for it. We assess to the standards in terms of what event may come along. Obviously things perform as they perform. In terms of tsunami risk, I think it's a risk. I'm not sure what the outcome of that is, personally, but I think it's relatively low because it's in a harbour and protected.
Okay, I'm going to hold it there. Could I ask you to thank all our speakers one last time?